Welcome to This Explainer. Today, we're diving straight into a massive challenge in generative AI right now: how artificial intelligence is actually learning to verify its own logic, completely without human handholding. If you've been following the explosive growth of large language models, you know they're brilliant, right? But they can also confidently hallucinate. Now, the traditional fix for this is heavy human intervention. But what if the AI could just verify itself? So, to set up our detective narrative today, we've got to ask a fundamental question. How on earth can we teach an AI to grade its own homework when human supervision is just so incredibly expensive? Right now, building highly accurate AI means teams of human experts are painstakingly grading the AI's step-by-step logic. It's a huge bottleneck. Finding a way around this human grading process isn't just a neat trick, it's absolutely critical if we're going to scale AI to solve complex, previously unsolved problems. Here's our roadmap for the explainer today. 1. The AI reasoning bottleneck. 2. Enter the Lover framework. 3. 3 rules of logic. 4. Putting Lover to the test. And 5. The future of AI. Let's jump right in. Starting with section 1, the AI reasoning bottleneck. Okay, let's explore this massive roadblock that's currently holding back state-of-the-art AI. Just to make sure we're all on the same page, we need to understand that verifiers are really the engine of modern AI reasoning. See, when an AI tackles a complex math problem, it doesn't just make one wild guess. It actually generates multiple potential paths. The verifier is basically the judge that looks at all these paths and decides which one is the real deal. But typically, these verifiers are trained on heavily supervised datasets, meaning humans had to sit there and label thousands of right and wrong answers just to teach the verifier how to judge. You can kind of think of these supervised verifiers as students who desperately need expensive, time-consuming private tutors. I mean, annotating just one Olympiad-level math problem can take hours. But cost isn't the only issue here. There's also human bias. Human annotators usually prefer standard ways of solving a problem, like using coordinate math, and they might actually penalize an AI for finding an equally valid but maybe less intuitive geometric shortcut. Unsupervised learning, though, that is the holy grail. It's the purely self-taught student, an AI that finds its own valid paths without a human tutor constantly dragging it back to conventional methods. Which brings us to section 2, enter the Lover framework. This all builds into a really innovative solution called the Logic-Regularized verifier, or Lover for short. What's absolutely fascinating here is how the AI starts acting like a detective. For a given question, the LLM generates a bunch of potential solutions. Lover then takes each solution and creates 2 distinct versions. It slaps the text, "This is a true answer," onto one, and "This is a false answer," onto the other. Then, it feeds these statements right back into the AI to search for clues within its own hidden states. It's literally interrogating the model, asking, "Hey, if I force you to claim this is true, how do your internal neurons react? And what if I force you to claim it's false?" By doing this, Lover completely unlocks the black box. It peers straight into the LLM's internal beliefs to extract intrinsic knowledge. The researchers actually found that looking at the activations in the middle layers of the model, specifically around the 15th to 20th layers, yielded the absolute richest latent knowledge. It takes those hidden states, runs them through a simple neural network, and maps them to a probability, a binary latent variable, without ever touching the underlying LLM's core weights. And the best part? No human labels required. 0. Plus, it's compatible with pretty much any off-the-shelf white box LLM. Let's look at section 3, 3 rules of logic. Now, you might be wondering, how does it actually know if those internal states are pointing to a right or wrong answer without a human explicitly telling it? Well, it relies on a simple checklist of 3 logical rules. First up, negation consistency. Basically, an answer cannot be both true and false. The probabilities of those 2 opposing assertions have to equal 1. Second, intergroup consistency. Say the AI generates 5 different reasoning paths that all somehow lead to the exact same final answer, let's say 42. Those paths form a group. This rule says answers within the same group should get identical truth scores. And third, intergroup consistency. Out of all the different final answers the AI brainstormed, ultimately only one group is the truly correct answer. But here's the kicker. Neural networks really don't like rigid black and white logic. They need smooth gradients to learn effectively. So by softening these strict logical rules into probabilities, for example, using something called entropy regularization to make sure the model doesn't just lazily hand out uniform scores to everything, the neural network can be trained end to end. It learns to score reasoning paths entirely by forcing its internal hidden states to align with these natural laws of consistency. Moving right along to section 4, putting Lover to the test. Okay, theory is fantastic, but let's see the actual receipts, right? When we test the Quen family of models on the GSM-8K grade school math dataset, the data brilliantly illustrates how Lover helps smaller models punch way above their weight class. By applying this framework, a 7 billion parameter model achieves reasoning accuracy that is basically neck and neck with a massively larger, far more expensive 32 billion parameter model that's just relying on standard baselines. That is a real game changer. That specific boost translates to a 3.3% absolute accuracy gain, and that represents Lover's impressive advantage over standard majority voting. Now, majority voting is exactly what it sounds like. The AI generates a bunch of answers, and whichever final answer pops up the most wins. Simple, right? But Lover proves it's so much smarter than a basic popularity contest. By combining the frequency of the answers with the model's actual internal confidence scores, based on those hidden states we talked about earlier, Lover operates as a highly optimized, weighted voting method that actively listens to the model's intrinsic knowledge. Furthermore, as we pull out more and more candidate solutions from the LLM, you can clearly see Lover consistently outperforming other heuristic baselines, like Coty decoding. See, Coty decoding relies on the probability difference between output tokens, which makes it incredibly sensitive to the exact format of the output. If the model doesn't spit things out in a very specific step-by-step format, Coty decoding just falters. But Lover, because it looks deeply at those internal hidden states regarding the correctness of the assertion, it's far more robust and scales beautifully as you sample more solutions. This is where the data gets vital. When evaluated across 10 different datasets, covering everything from complex math to common sense reasoning to open domain knowledge, the results were stunning. Lover consistently beat unsupervised baselines. But more importantly, it proves our self-taught student is performing at 95% of the level of the student with the expensive private tutor. Reaching 95% of the supervised verifier ceiling without dropping a single dime on human annotation or explicitly labeled data, that is a massive breakthrough in efficiency. And that brings us to our final section, Part 5, the future of AI. Let's wrap this up by looking at why this research is such a huge leap forward for AI practitioners. By stripping away the need for human supervision, we aren't just saving an incredible amount of money and time, we are actively removing human annotator bias. The AI is now totally free to discover equally valid, diverse, and maybe even highly unconventional reasoning paths that a human tutor might have accidentally penalized it for. Plus, the research showed Lover has phenomenal out-of-distribution generalization. Because it's learning the underlying patterns of assertion correctness, rather than just memorizing domain-specific tricks, it can tackle completely novel logic puzzles it's never even seen before with remarkable accuracy. I want to leave you with this final provocative thought about the bleeding edge of artificial intelligence. Frameworks like Lover are showing us that the training wheels are officially coming off. We're moving away from an era where we have to explicitly spoon-feed AI what is right and wrong, and stepping into an era of self-verifying systems that can discover truth through their own internal logical consistency. If an AI can verify its own reasoning without us, what new, undiscovered truths might it uncover next? Thanks for joining me on this explainer, and keep questioning the logic.